Hello, my friends. Thank you very much for subscribing to our channel. The meaning of golden ratio is the summation of two positive numbers over the bigger one is equal to the bigger one over the smaller one. Its value is equal to the square root of 5 plus 1 over 2. We denote the inverse of the golden ratio as phi, which is equal to the square root of 5 minus 1 over 2. And we also know that it is equal to 1 minus the square of itself. We have a rope whose length is 1. We cut it into two parts. The longer part is phi, which is one of the parts, and further cut it into another two parts. The longer part after the cut, over the part before cut, is always equal to phi. We can iterate the operation in this way, and denote the number of segments obtained after each cut as k. And the length of the longest segment is denoted as Lk. So what is the minimum value of k times Lk? Why not give a try, and we will come back soon. Let's first take a look at how to make the product of k times Lk as small as possible after each cut. For the first step, there is no other option but to cut the rope into phi and the square of phi. The second time, we have to choose. No matter cutting phi or cutting the square of phi, the result is always 3 segments. That is to say, k is always equal to 3. So we must make the Lk as small as possible. That is to say, we need choose the longer one which has the length of phi. The two segments cut out have the lengths phi times phi and phi times the square of phi respectively. That is, the square of phi and phi to the third power. The third segment has the length of the square of phi, which is left over from the previous cut. At this time, the longest segment has the length of the square of phi. So for the third time, we are going to cut this one. But at this time, there are two segments have the same length of the square of phi. If only one of them is cut, only k is increased by 1, but Lk is not decreased. So the result must become bigger. Therefore, only cutting once at this time doesn't make any sense. Rather we have to add another cut so as to cut the both segments with the length of the square of phi. The result is 2 segments of phi to the third power, and 2 segments of phi to the fourth power. Certainly, please don't forget that there is still a segment of phi to the third power left over from previous cut. Till now, we have come to a conclusion that, if we expect the result after some cuts does not necessarily increase, we shouldn't consider the cuts in a one-by-one manner. Rather we should consider them group by group. In each group, we need to cut all the longest segments which actually have the same length. Obviously, in this group, we cut them twice. There are now 3 segments, which have the longest length of phi to the third power. So in the next group we are going to have 3 cuts. Therefore, we get 3 segments with the length of phi to the fourth power, and 3 segments of phi to the fifth power, as well as the 2 segments of phi to the fourth power left from the previous cuts. Let's check what we have learned now. In the first group, there is 1 cut. The longest length is phi to the first power, for 1 segment. In addition, there is also phi to the second power. In the second group, also 1 cut. The longest length is phi to the second power, for 2 segments. In addition, there is a segment of phi to the third power. In the third group, there are 2 cuts. The longest length is phi to the third power, for 3 segments, including the 2 segments cut out in this group, and the 1 left before. In addition, there are 2 segments of phi to the fourth power. In the fourth group, there are 3 cuts. The longest length is phi to the fourth power, for a total of 5 segments, including the 3 segments cut out in this group, and the remaining 2 segments left before. In addition, there are 3 segments of phi to the fifth power, and so on. So in the group M, there should be Fm cuts. The longest length should be phi to the mth power, including 2 parts. One part is the Fm segments cut out in this group, and the other part is the Fm minus 1 segments left over from the previous cut. In addition, there are also Fm segments with the length of phi to the power of m plus 1. In the group m plus 1, the longest length should be phi to the power of m plus 1. Among those segments, Fm plus Fm minus 1 segments are cut from the previous segments, which used to have the length of phi to the nth power after the previous group of cuts. That is to say, fm plus 1 is equal to fm plus fm minus 1. So the amount of cuts in each group is indeed the famous Fibonacci number. We use the situation after the mth group of cuts for the further analysis. At this time, the longest length is phi to the mth power. And there are a total of double fm, plus fm minus 1 segments. That is, fm plus 1, plus fm segments. We have explained that, after the cuts for the times which are the same as this first mth groups of cut, no other ways will result in the value of k times Lk shorter than the cut in this manner. Therefore, finding the particular m that corresponds to the minimum value of this expression will result in the minimum value of k times Lk. There is one condition we shouldn't forget, that is the summation of the lengths of all segments will not change for any cut, but remains 1. We write phi to the power of m plus 1, as phi to the power of m, and multiply by phi. Don't forget that, phi is equal to 1 minus the square of phi. So our goal can be written as 1 plus fm times phi to the power of m plus 2. To find the minimum value of 1 plus fm times phi to the power of m plus 2, we just need to find the minimum value of fm times phi to the power of m plus 2. We need to insert a few unnecessary words here. When people see fm multiplied by phi, it is so straightforward to think of the topic, regarding the relationship between the limit of the ratio of adjacent two Fibonacci numbers. As m approaches infinity, if there is such a limit, fm plus 1 over fm is equal to fm over fm minus 1. That is to say, fm plus fm minus 1 over fm is equal to fm over fm minus 1. Obviously, this is the definition of golden ratio. However, as a math challenge for the students from the 9th grade, this topic is obviously beyond the background knowledge at this level. And actually it is also not necessary for solving the problem. So we don't really go to this way. Then how will we make it? We can list a few m first, and check what results we can get. When m is equal to 1, it is equal to phi to the third power. When m is equal to 2, it is equal to phi to the fourth power. This is smaller than phi to the third power as phi is smaller than 1. When m is equal to 3, it is equal to twice phi to the fifth power. Because twice phi is equal to the square root of 5 minus 1, which is bigger than 1. So it's bigger than phi to the fourth power. Up to now, the minimum value is still phi to the fourth power. When m is equal to 4, in a similar way, we get, it is equal to 3 times phi to the sixth power, which is still bigger than phi to the fourth power. So is the minimum value really phi to the fourth power? We can prove it by using mathematical induction. We have known that, when m equals 3, both fm times phi to the power of m plus 2, and fm plus 1 times phi to the power of m plus 3 are bigger than phi to the fourth power. So we are going to prove that, fm plus 2 times phi to the power of m plus 4 is also bigger than phi to the fourth power. We first write fm plus 2 as fm plus 1, plus fm. The former part is written as fm plus 1 times phi to the power of m plus 3, times phi. And the latter part is written as fm times phi to the power of m plus 2, times the square of phi. The former part is bigger than phi to the fourth power, multiplied by phi. And the latter part is bigger than phi to the fourth power, multiplied by the square of phi. Putting them together, we get phi to the fourth power, times phi plus the square of phi. And, phi plus the square of phi is indeed 1. So the proof is done. Then the minimum value of the target is indeed 1 plus phi to the fourth power. Bring in the value of the square root of 5 minus 1 over 2. The final answer is 9 minus 3 times the square root of 5 over 2. Thank you for watching, and see you next time.